Greetings of the day to all of you. In today's lecture, we are going to start our discussions on series compensators. Over last 4 to 5 lectures, we have been discussing about various types of shunt compensators. The main shunt compensators that we have discussed in last 4 to 5 lectures were thyristor-based shunt compensator, which is SVC, and converter-based shunt compensator, which is STATCOM. And we have also tried to make a comparison or comparative analysis between the two types of shunt compensators. From today onwards, for a few lectures, we are going to discuss variable impedance series compensators. I will write here variable impedance series compensators. So in other words, our future lectures, including today's lecture, will be about the discussion of various types of series compensators, which are also called variable impedance series compensators. Various types of series compensators, I have already given you a list of various types of series compensators like Gcse, TSSC, TCSC, SSSC, etc. So today we are going to discuss the first type of series compensator, that is GTO controlled series capacitor. GTO controlled series capacitor. GCSC. It's a series capacitor which uses GTO valves, GTO power semiconducting devices. It does not use IGBTs. It exclusively uses GTOs, gate turn-off thyristors. Okay, now this GCSC, that's GTO controlled series capacitor, it was first of all proposed by a researcher, Karady or Karady et al. Et al means other authors, other researchers who have worked along with Dr. Karady. So Karady et al., they proposed this GCSC first time in 1992. So way back in 1992, it was proposed by Karady et al. Okay, and it looks like this. We have a bidirectional switch comprising of anti-parallel connected pair of GTOs, gate turn-off thyristors, like this, and in parallel to this we have a capacitor, fixed capacitor C. The current, this is your transmission line, the current in the transmission line is I, and in series with the transmission line you are basically connecting this switch S, which comprises of GTO G1 and GTO G2, which are anti-parallel connected to each other, and across this GTO switch S we have a capacitor C. The voltage across capacitor is Vc, for example. Now, what is the aim of this GCSC? The aim of this GCSC is to control the voltage across capacitor, to control voltage across capacitor Vc. Okay, this we want to control. See, if you put a fixed capacitor in series with transmission line, then for a given transmission current, the voltage across capacitor will be fixed. For example, this may be your transmission line current, this is capacitor, and voltage across capacitor is fixed Vc. In order to make it variable voltage or controllable voltage, and hence to make this capacitor along with this switch, bidirectional switch, a variable impedance series compensator, which puts a variable voltage in series with the transmission line. What we are doing, this capacitor, across this capacitor we are having a bi-directional switch, which basically comprises of anti-parallel connected pair of GTOs like this. The switches are G1 and G2 like this. So by turning on and off of these GTO switches, GTO valves, we can make this voltage across the capacitor as variable voltage. How does it work? When the switch S is on. So when this switch is on, for example, for positive current, GTO G1 is turned on, and current flows in this direction, and for negative direction of current, G2 is turned on, current flows in this direction. That means when the switch S is turned on, we know that when a power semiconducting device acts as a switch, and when the switch is closed, okay, the voltage across switch is 0. So therefore voltage, since capacitor is connected across the switch, the capacitor voltage is 0. So that means when the switch is closed, capacitor voltage is 0. The voltage across capacitor is 0. And when switch is opened, or when switch is off, means neither G1 nor G2 is triggered, G1 is off, G2 is off, all this transmission line current flows through this capacitor, and it causes maximum voltage across the capacitor. So capacitor voltage appears across the capacitor, and that is the maximum voltage. So therefore, by controlling the turning on and turning off of this GTO switch in a controlled manner, the voltage across the capacitor can be controlled from 0 to Vc max. So voltage across the capacitor can be controlled from 0 to Vc max. When switch S is permanently on, voltage across capacitor is 0, Vc is equal to 0, and when it is permanently off, the voltage across capacitor is Vc max. And by controlling the switching on and off of the GTO switch, G1 and G2, a variable voltage V can be achieved. Voltage across capacitor can be made variable, and it can be made to vary from 0 to Vc max, or Vc max to 0. So a variable voltage across capacitor appears, and that voltage is in series with the transmission line, and hence your Gcse works as a variable impedance. Okay, so this is basic principle of operation. Now you should remember that the GTO valve is closed, means turned on, when capacitor voltage crosses 0. Whereas in a TCR, if you compare it with the TCR, thyristor valve is opened in a TCR when current crosses it is 0. And the turning off of GTO valve is controlled by controlling the turn off delay angle. So I will write here one statement, that is turning off of Gcse is controlled by controlling the turn off delay angle, turn off delay angle gamma with respect to the peak or crest of current I, and the range of this gamma, the range of turn off delay angle gamma, is 0 to pi by 2. This will be clear to you with the help of a couple of waveforms. Let me show you a couple of waveforms. This is omega t. This is, for example, current, transmission line current. So this is transmission line current I. Let me draw the circuit diagram again. This is GTO switch G1, and this is GTO switch G2, and this is transmission line current I, and this is capacitor C. Voltage across capacitor is Vc, and this is the bidirectional switch S. This is the transmission line current I. Now if switch S is permanently on, that means we don't turn it, if this switch S is permanently off, we don't turn it on again, we don't turn it on at all, it is permanently off, then all the current will flow through the capacitor, and maximum voltage will appear across the capacitor, and that voltage will lag behind current because it is a capacitive circuit. In a capacitor, current leads the voltage by 90 degrees, or in other words, voltage lags behind the current by 90 degrees. So it will be something like this. This is pi, 2 pi, and so on. So this is the voltage across capacitor. This is Vc, and it is maximum voltage. And in this case, we can say gamma is equal to 0 degree. Gamma is basically turn off delay angle. I mean, it is the phase angle, or it is the angle by which the turning off of switch S is delayed. Here we don't delay it. At the crest or peak of the current itself, we turn off the switch. The switch is turned off. Let us assume previously the switch was on, and when the switch was on, all the current was flowing through the switch. And what was capacitor voltage? Capacitor voltage was 0. And then we turn off the switch at gamma equal to 0 degree. So gamma omega t equal to 0 degree means basically omega t equal to 90 degree basically means gamma equal to 0 degree, because the turn off delay angle is measured from crest of or peak of the current to this, that is pi by 2 to pi, or it has a range. If this is taken as 0 to pi by 2, total range is 90 degrees. So GTO is turned off. So GTO switch or valve switch S is turned off here at gamma equal to 0 degree, and it permanently remains off. When it permanently remains off, all the current flows through the capacitor and maximum voltage appears across the capacitor. This is the maximum capacitor voltage. On the other hand, if we increase this turn off delay angle by certain degrees, let me show you that in next waveform. This is again transmission line current I, and this is peak. These are the peaks of the current waveform, crest of the current waveform. Okay. Now let us assume that previously GTO switch is on. Since current is positive, positive current means G1 is on. So G1 switch is on. So current is flowing in this direction, and since G1 is on, current is flowing, positive current is flowing in this direction. What is voltage across the capacitor? Capacitor voltage is 0 because it is shorted by the switch. So voltage across capacitor is 0. And we don't turn off the switch here. We delay its turn off by say 20 to 30 degrees. Let me redraw this. Waveform. Let me zoom it a little bit. This is transmission line current I. Okay, so these are the crests or peaks of the current: positive peak, negative peak, and then again positive peak and negative peak. Previously, what is happening here? GTO, since current is positive, G1 switch is on. Let's assume G1 is on. So G1 is on. G1 is on. And we do not turn off G1 at the peak of the current. We delay its turn off. We delay its turn off, let's say, by 30 degrees. So from here to here, G1 is on, and this is omega t equal to 0. So from this omega t equal to, this is taken as omega t equal to 0. The crest of the or peak of the current is taken as the reference for measuring turn off delay angle. So from here to here, this is turn off delay angle gamma. Let us assume this gamma is around 30 degrees. So here, when gamma is 30 degrees, GTO switch S1, G1 is turned off. How is it turned off? Turned off by removing the gating current from its gate, by making gating current at its gate terminal equal to 0. So it immediately turns off. As soon as it immediately turns off, the whole current I starts flowing through the capacitor, and voltage starts building across the capacitor. So there will be voltage build up across the capacitor like this. Voltage will build up across the capacitor, it will rise and then it will fall. So this period, this is gamma, this is sigma. This period is called sigma, that is blocking period. Blocking angle is the angle during which GTO switches off. And when GTO switches off, all the current flows through the capacitor, because the GTO switches off, it blocks the current. Current has to flow through the capacitor, and voltage appears across the capacitor. This is the capacitor voltage Vc. And as soon as voltage across capacitor becomes equal to 0, then G2 is turned on. You can see, since current is the negative, you have to now turn on G2. So G2 is turned on, and current is in the negative direction, reverse direction, it flows in this direction, and Vc again becomes equal to 0. यहाँ से यहाँ तक, this is next reference for measuring gamma. Gamma is 30 degrees, तो यहाँ से यहाँ तक आपका जो है G2 on. लेकिन यहाँ से यहाँ तक, from this instant to this instant, G1 is off. G1 is off. G1 was earlier on, so voltage across capacitor was 0 during this period instant, and from this instant to this instant, G1 is off. So all the current flows through the capacitor and voltage appears across the capacitor. So during this period, G1 is off. And here, as soon as your voltage becomes equal to 0, G1 is turned off. Okay, so sorry, G2 is turned on. G2 is turned on, current flows in the reverse direction, and voltage again becomes equal to 0. Voltage across capacitor again becomes equal to 0 because it is flowing through G2. And then here, G2 is turned off by making its gate current equal to 0, and as soon as G2 is turned off, all the negative current flows through the capacitor, and a negative polarity voltage appears across the capacitor like this. This is the voltage across capacitor Vc. And during this period, यहाँ से यहाँ तक आपका G2 ऑफ है, and then it repeats. फिर आपका यहाँ से यहाँ तक G1 again on है. G1 is on again because current is positive, so current has to flow. Positive current always flows through G1, and then again G1 is off. यहाँ से यहाँ तक G1 फिर से off है, and it continues like that. So this is the nature of voltage across across the capacitor. Now in the previous case, when gamma was equal to 0, let me redraw that waveform. When gamma was equal to 0, this was your current, transmission line current, 0, pi, and so on. Gamma equal to 0 means this is gamma equal to 0. At gamma equal to 0 itself, previously G1 was on. G1 was on, and all the positive current was flowing through the G1, and Vc was equal to 0. And at omega t equal to 0, which is gamma equal to 0 degree, G1 is turned off. G1 is turned off means all the voltage, all the current is flowing through this capacitor, and it is kept off permanently. So voltage appears across capacitor like this. This is the voltage across capacitor. This is capacitor voltage Vc, and you can see during this period, यहाँ से यहाँ तक G1 off है, and negative half cycle of current में पूरे में G2 off है. Then negative half cycle of current, yes, G2 off है, और फिर पॉजिटिव हाफ साइकिल करंट का आ जाता है. इस दौरान G1 परमानेंटली ऑफ है, एंड देन आई मीन यू आर टर्निंग ऑफ G1 here, and G1 G2 both are permanently off, and all the current, whether it is positive current or negative current, it flows through the capacitor, and maximum voltage appears across the capacitor. So Vc is equal to Vc max. Okay, and if you make gamma equal to 30 degrees, instead of turning off GTO switch here, you are delaying its turn off by 30 degrees. This is the nature of voltage which will appear across the capacitor. This is Vc, and of course this is less than this. So therefore, larger the turn off delay angle, smaller will be this zeta. You can see this zeta. Zeta is it's called blocking angle. Blocking angle is given by this angle zeta. And you can see from the waveform, it is pi minus 2 gamma. Pi minus 2 gamma, because this is gamma. Okay, and as turn of delay angle gamma increases, the blocking angle decreases. और जितना blocking angle decrease हो जाएगा, उतना capacitor voltage decrease हो जाएगी. Because voltage appears across the capacitor only when the switch is in the off position, when it is in the blocking position. The period for which the switch is blocked, if that period is large, then voltage across capacitor is small. Okay, the period for which this switch is on, if that is large, then voltage across capacitor will be small. Okay, and the period for which this switch is off means gamma sigma is more, the capacitor voltage is more, voltage across capacitor is more. अब यहाँ पे आप देख सकते हैं as gamma increases, sigma decreases. Sigma decreases मतलब ये voltage कम हो जाती है, voltage across capacitor decreases. So as gamma, turn off delay angle increases, the blocking angle decreases. And from this equation, as blocking angle decreases, you can see from the waveform, the voltage across capacitor decreases. Capacitor voltage decreases, right? Now, I have already told you that the range for this gamma is 90 degrees to 180 degrees. अगर इसको आप 90 डिग्रीज को 0 डिग्री रेफरेंस मानेंगे, सो इट इज 0 to 90 degrees. Okay, this is 0, this is 90 degrees. Total range is 0 to 90 degrees. और अगर आप with respect to this देखिए, with respect to this zero crossing, it is 90 to 180 degrees. Why can't we have, can we have this turn off delay angle gamma less than 90 degrees? Answer is no. Why? Let me explain that. So range of turn off delay angle gamma is 90 degrees to 180 degrees. That is crest of current to here, 90 degrees to 180 degrees, pi by 2 to pi. What about gamma less than 90 degrees? Is that possible? Let us try to see whether we can have gamma less than 90 degrees. Again, this is our transmission line current I. If gamma is less than 90 degrees, that means previously आपका GTO switch, since current is positive, let us assume GTO switch G1 was on, यहाँ से यहाँ तक G1 on, and I am making now gamma less than 90 degrees. Gamma less than, ये 90 degrees है, less than 90 degrees means GTO switch, instead of turning it off here or beyond this point, I am turning it off earlier, less than 90 degrees. As soon as this switch is turned off, all the current then gets bypassed through the capacitor and voltage appears across the capacitor. And this is the voltage which appears across the capacitor. It increases and then it decreases. Now positive half cycle mein, this is gamma less than 90 degrees. Here G1 switch is turned off, G1 is turned off. Then negative half cycle में आपका G2 पहले on होना चाहिए, फिर off होना चाहिए. If in the positive half cycle you are turning off, this is gamma, आपका gamma इतना है 60 degrees. Negative half cycle में आपका gamma इतना होना चाहिए. That means यहाँ negative half cycle में आपका G2 यहाँ off होना चाहिए. G2 पहले on होना चाहिए, फिर off होना चाहिए. But the problem is that your G2 does not, G2 off तब होगा जब ये on हुआ था. It does not get a chance to turn on. It's not turning on at all. Okay? Why? Because voltage across capacitor was earlier increasing and then it is decreasing. So it is rising, which is showing energy stored in the capacitor, and then it is falling, which shows energy released by the capacitor. And the energy stored by the capacitor should be exactly equal to energy released by this. So therefore you are not turning off, you are not turning on G2 at all. It's already off. By convention you had to turn it on here, turn it off here, but it's already off. Okay, in the next positive half cycle again G1, now let us assume G1, यहाँ इसके बाद G2 आप ऑन करते हैं, फिर G1 भी ऑन करते हैं, G1 यहाँ ऑफ होता है, तो ये आपकी वोल्टेज है. So therefore capacitor, because of this limitation, you can see the capacitor voltage even if it is discrete, it is not continuous, it should be AC. Its average value should be 0. It should not have any DC component, which is true here. But in this case, what type of capacitor voltage are you having? You are having a capacitor voltage which has only positive excursions. It does not have negative pulsation, negative excursion. So a very strong DC component will be there across the capacitor voltage. So capacitor voltage will have a very strong DC component. This capacitor voltage will be AC. It will be DC, not AC. Whereas capacitor voltage, since it's connected across in series with the transmission line, and transmission line current is AC, it should also have been AC like this. But if gamma is less than 90 degrees, then capacitor voltage has a very strong DC component. That is why gamma less than 90 degrees is not possible. Gamma less than 90 degrees, not possible. So therefore, minimum value of gamma is 90 degrees, 90 to 180 degrees, or you can say 0 to 90 degrees. So this is the range of gamma. That's turn off delay angle. Now, in the next waveform, I will show you how by controlling the turn-off delay angle, we are able to control the voltage. Okay, let me show you. So, voltage control is achieved by gamma control. Okay, and gamma is controlled from 0 degrees, gamma equal to 0 degrees to gamma equal to 90 degrees. For gamma equal to 0 degrees, maximum voltage will be there across the capacitor because your GTO valve will be permanently off. And for gamma equal to 90 degrees, your GTO valve will not turn off at all. It will be all the time on. So voltage is 0. And in between from 0 to 90 degrees, the voltage across capacitor will be variable. It can be summed up in the form of a single waveform like this. A single waveform can explain this phenomenon. This is transmission line current I. This is 0, pi, 2 pi, and so on. I will again draw the Gcse circuit diagram. This is GTO valve G1. This is GTO valve G2. This is transmission line current I. This is capacitor across this GTO valve, and voltage across capacitor is Vc. Right. I have already told you that gamma is measured from 90 degrees, from crest or from peak of the current. Okay, let us assume gamma is equal to 0 degree. And gamma equal to 0 degree, that means your GTO is not turned on at all. It's off. It's permanently off. And since it is it's off, okay, it is turned off at gamma equal to 0 degree. Maybe previously also it was off. So, or let us start from here. At gamma equal to 0 degree, all the firing pulses or control pulses are withdrawn from G1 and G2. So both the devices are off. So that means this GTO switch S is off. All the current is flowing through this capacitor, and voltage across capacitor is maximum, and it is like this. Since it is a capacitive circuit, voltage will lag behind the current by 90 degrees. Or in other words, current will lead the voltage by 90 degrees. So this is it. Okay, and then let us assume that here GTO you see here GTO G2 should, if you keep GTO G2 off permanently, then negative current, it will flow through this capacitor, and it will result in negative voltage across this capacitor. Negative voltage across the capacitor, voltage will be negative. लेकिन अब हम क्या करेंगे? Let us assume that GTO G2 is turned on. यहाँ से यहाँ तक G2 on करते हैं हम. G2 is on from when GTO G2 is on. Why G2 is turned on? Because current is having negative excursion. Current is negative, and negative current will be carried by G2 only. G1 carries positive direction of current, and G2 carries negative current. So G2 for some time is turned on, and then here after gamma, see here gamma was 0. G1 was turned off at gamma equal to 0. Here G2 is turned off after say 30 degrees. Or let us call this gamma equal to gamma 1. ये angle यहाँ से यहाँ तक. G2 is turned off. यहाँ मैं लिखूँगा G2 अब off हो रहा है आपका. जो ही G2 आपका off हो रहा है, all the current flows through the capacitor, and a negative voltage appears across the capacitor. Because current is negative, the negative voltage will appear across the capacitor. It will reach its peak value, and then it will come down. So during this period, यहाँ से यहाँ तक आपका G2 और G2 value G2 is off. That's why all the current is flowing through capacitor and negative voltage appears across the capacitor. Next positive half cycle में मैं क्या करूँगा? I will further increase this turn off delay angle. So here it was gamma 1. Let us assume here it is further increase. Gamma is equal to gamma 2. लेकिन यहाँ से यहाँ तक G1 आपका on कर रहे हैं हम, क्योंकि current positive है, मैं चाहता हूँ यहाँ से यहाँ तक G1 on हो जाए and current flows through G1 and capacitor voltage becomes 0. You can see from here to here G1 is on, capacitor voltage is 0, and then G1 is turned off at gamma equal to gamma 2. Here G1 is turned off here, यहाँ और जो ही G1 ऑफ हो जाता है ये करंट कैपेसिटर के थ्रू फ्लो होती है and it results in voltage, positive and negative voltage. और during this period यहाँ से यहाँ तक आपका G1 ऑफ रहता है. उसके बाद G2 हम फिर ऑन करते हैं. You can see G2 फिर से ऑन करते हैं और अब मैं G2 को ऑफ करूंगा gamma equal to gamma 3 पे, which is greater than gamma 2. Say somewhere here. This is gamma equal to gamma 3, which is greater than gamma 2. और यहाँ से यहाँ तक आपकी करंट चूंकि नेगेटिव है और कैपेसिटर वोल्टेज में 0 दिखा रहा हूँ. कैपेसिटर वोल्टेज will be 0 only when G2 value is on. And which G2 value will conduct? G2 will conduct. So during this period, G2 value is turned on, and then it is turned off here. As soon as it is turned off, a negative, small negative voltage will appear across it. Okay. उसके बाद चूंकि करंट पॉजिटिव है, आपका G1 ऑन है और मैं गामा इक्वल टू 90, हियर गामा इज इक्वल टू 90 डिग्रीज. 90 डिग्री मतलब है मैं G1 को यहाँ ऑफ करता हूँ, बट इट इज़ ऑलरेडी ऑफ. सो देयरफॉर उसके बाद जब G1 यहाँ ऑन रहता है, ये ऑन ही रहता है क्योंकि गामा इक्वल टू 90 डिग्रीज पे आई वांट टू टर्न द वैल्यू ऑफ, बट इट इज़ ऑलरेडी ऑन, इट डज नॉट टर्न ऑफ, एंड देन दिस इज इट. So therefore gamma equal to 0 degree पे this is your capacitor voltage. Capacitor voltage is maximum. उसके बाद gamma equal to gamma 1 is greater than 0 degree, voltage कम हो जाती है. उसके बाद आप gamma 2 further next half cycle में you increase gamma from gamma 1 to gamma 2, where gamma 2 is greater than gamma 1, voltage फिर से कम हो जाती है. Next half cycle में आपका turn off delay angle है gamma 3 which is greater than gamma 2. वोल्टेज फर्दर कम हो जाती है टिल यू रीच गामा इक्वल टू 90 डिग्रीज. एट गामा इक्वल टू 90 डिग्रीज आपकी वोल्टेज अक्रॉस द कैपेसिटर इज 0 बिकॉज योर G2 इज परमानेंटली ऑन, इट डज नॉट टर्न ऑफ एट ऑल. ओके, सो इन वन डायग्राम एक्चुअली प्रैक्टिकली वी डोंट डू लाइक दिस. एक ही साइकिल में ये नहीं करते, पहले हाई फिर लो. दिस इज जस्ट टू एक्सप्लेन. फॉर फ्यू साइकिल्स योर गामा में बी 0, then depending upon the requirement कि आपको कितनी कैपेसिटर वोल्टेज चाहिए, you may reduce gamma from gamma to gamma 1 and it may remain there for number of cycles. Then you may further increase gamma from gamma 1 to gamma 2 after many cycles and keep it like that and so on. So this one diagram shows that as gamma is increased from gamma equal to 0 degree to gamma 1 to gamma 2 to gamma 3 to 90 degrees, the voltage across capacitor keeps on decreasing till gamma becomes equal to 90 degrees. At gamma equal to 90 degrees, the voltage across capacitor Vc becomes equal to 0. So this means that as gamma is increased, voltage across capacitor decreases till at gamma equal to 90 degrees, capacitor voltage is 0. Okay, at gamma equal to 0 degree, capacitor voltage is maximum, Vc max. और फिर as you increase gamma from turn off delay angle, gamma from 0 degree towards 90 degrees in small intervals, Vc decreases. Capacitor voltage linearly decreases till you reach gamma equal to 90 degrees, at which Vc is equal to 0. That's capacitor voltage becomes equal to 0. Let me show you the firing pulse pattern of this Gcse. So the firing pulse pattern is something like this. This is again transmission line current I. Okay, and let us assume these are peaks or crests of the current which are references for turn off delay angle. Let us assume turn off delay angle is this much. This is gamma, turn off delay angle. And this is your capacitor voltage for a fixed turn off delay angle. This is the capacitor voltage Vc. Okay, what is the pattern for firing pulses or gating pulses for GTOs? So Ig1, that is the gating current pulse for G2 or G1. It will be like this. Let me first of all draw it, then I will explain it. It will be like this permanent pulse like this. The next pulse will be from here to here. Similarly, gating current pulse Ig2 for G2's value G2. When this pulse is high, this pulse is low, and when this is low, this will be high, like this. और फिर यहाँ से यहाँ तक. It will be again high. Now it is very interesting to see. See here, your G1 is on, and when current is positive, so it has to flow through G1. तो आप पहले G1 को on रखते हैं, आप इसको control pulse देते हो यहाँ तक. और यहाँ तक G1 on है, all the current is bypassed through G1, no current flows through the capacitor, and since current is flowing through G1, the switch is on and voltage across capacitor is 0. You can see Vc is equal to 0 during this period. और यहाँ पे gamma equal to say 10 or 20 degrees पे आप gating pulse G1 की low करते हो, you make it low. जो ही आप इसको लो करते हो G1 ऑफ हो जाता है, लेकिन करंट भी पॉजिटिव ही है. वो पॉजिटिव करंट किसके थ्रू आप फ्लो होगी? वो दैट कैन नॉट, ऑल्दो योर कंट्रोल लॉजिक सर्किट इज इशूइंग गेटिंग पल्स टू G2, बट करंट कैन नॉट फ्लो थ्रू G2 बिकॉज इट इज हैविंग दिस डायरेक्शन. This direction of current will flow only through G1, and when G1 is turned off here, so the remaining portion of the current, a positive current, ये कहाँ से flow होगी? It will flow through the capacitor, and it will result in voltage, positive voltage across the capacitor यहाँ से यहाँ तक, क्योंकि यहाँ से यहाँ तक आपका G1 off है. उसके बाद आपका जो ही capacitor voltage 0 हो जाती है. Okay, that means capacitor has released all the energy, whatever charge or whatever energy it had stored, it is releasing. So capacitor voltage is 0. Your control logic circuit immediately issues control pulse to G2 or G2. Okay, वो तो already इसने यहीं पे दी थी, और ये लेकिन यहाँ से यहाँ तक जब तक G1 on है, G2 on नहीं हो सकता तब तक. और जब G1 off हो जाता है, see, जब तक G1 off है, when G1 is off, all the current is flowing through the capacitor, and when voltage across capacitor becomes 0, your control logic circuit should issue control pulse to gate to this G2, and as soon as Vc becomes equal to 0, G2 turns on, and since current is negative, ये negative current immediately G2 के through flow होगी और voltage फिर से 0 हो जाएगी, voltage across capacitor 0 हो जाएगी. Till this point, at this point G2 की कंट्रोल पल्स देखिए लो हो जाती है. जो ही G2 की कंट्रोल पल्स लो हो जाती है, G2 ऑफ हो जाता है, और जो ये नेगेटिव करंट का पोर्शन है, ये कैपेसिटर के थ्रू फ्लो होता है, एंड स्मॉल नेगेटिव वोल्टेज अपीयर्स अक्रॉस द कैपेसिटर एंड सो ऑन. सो दिस इज द गेटिंग पैटर्न or gating pulse pattern for this GCSE valve, GTO valves G1 and G2, IG1 and IG2. Okay, and now we can see this is the capacitor voltage, positive capacitor voltage BC. This is the negative capacitor voltage, यहाँ से यहाँ तक you can see. And when capacitor voltage is positive, what is current? Current उस वक्त ये है. This is the current. It is here. It is this much, and then it decreases. Or here it is this much. So this is the nature of current. I can show current with a red color pen. It is like this. This is current through the GTO valve. This is current through GTO valve. Sorry, this is current through the capacitor. When does voltage appear across the capacitor? When current is flowing through it. This is voltage across capacitor, and current, nature of current which is flowing through the capacitor is this. You can see it from here. ये है current through the capacitor, and voltage across. Similarly, in the negative half cycle, if this is the negative half cycle of voltage across capacitor, what will be current through the capacitor? ये होगी current through the capacitor. You can see negative, positive. So this will be current through the capacitor, negative and the positive, like this. Similarly, you have another positive half capacitor voltage, and you have negative half capacitor voltage, and currents are again positive, negative, and negative, positive. So this shows voltage that when current is flowing through the capacitor, whether it is positive or negative or like this, This is the voltage across capacitor. When voltage across capacitor is positive, this is the current through the capacitor. When voltage across capacitor is negative, this is the nature of current through the capacitor. Okay. Now let us derive a simple mathematical expression for current through the capacitor, voltage across the capacitor. Okay. Now voltage across capacitor Vc is given by Vc is equal to 1 by C integral gamma to omega t it dt, because voltage across capacitor is 1 by C integral I dt, and you have to take when does voltage appear across the capacitor? When the GTO valve is off, and GTO value कहाँ पे आप off करते हो? At turn off delay angle gamma to omega t. When gamma is equal to, when turn off delay angle is gamma, at gamma omega t equal to gamma, you turn off the GTO value and all the current flows through the capacitor and voltage appears across the capacitor from the time interval gamma to omega t. Okay, so Vc will be equal to 1 by C integral gamma to omega t. And what is the nature of current through the capacitor? I will again draw, for example, again positive current voltage across capacitor. Current is like this. Current already peak pe hai. When voltage is 0, current is at its peak. So it is given by I cos omega t dt. Okay. So current expression is not I sin omega t. I is the peak of the current. It is I cos omega t, because at omega, this is gamma, when GTO value is turned off, the voltage is 0, current is already at its peak value, and previously current I say t, sinusoidal I say t, I say. So here the equation is I cos omega t. So Vc is equal to I bahar nikaliye by omega c. What is the integration of cos omega t with respect to t? It is sin omega t. Let me write 1 by I by c integration sin omega t from gamma to omega. What is the integration of cos omega t with respect to t? It is sin omega t by omega. वो omega में बाहर निकालूंगा. So therefore Vc is equal to I by omega c into ये limits आप इसमें डाल दीजिए sin omega t minus sin gamma. And if you still remember the theory of TCR, that is the controlled reactor, this equation is similar to the current through TCR. For example, the voltage across capacitor VCT, which is a function of gamma. It is a function of gamma, as you can see. It is given by this equation, I by omega c into sin omega t minus sin gamma. We have derived it just now. And for a TCR, current through the TCR IL, which is a function of alpha, if you remember, that is given by V by omega L. In place of current, there it is voltage. In place of C, it is L into sin omega t minus in place of gamma, it is alpha minus sin alpha. So therefore, this equation is similar. The equation for current flowing through a TCR, which is a function of alpha, is given by V by omega L into sin omega t minus sin alpha, and the voltage across capacitor in case of a GCSE, which is a function of gamma, is given by I by omega c times sin omega t minus sin gamma. So these two equations are, you can say, these two equations are analogous to each other. Okay, or there is a duality between the two. There is, I will write here, duality between Gcse and Tcr. In Gcse, here it is I, in Tcr it is V. C here it is L. What is the dual of C? Dual of C is L. What is the dual of I? It is V. What is the dual of gamma? It is alpha. So the two equations are dual. So therefore Gcse and TCR are dual to each other. They are dual to each other. Okay. Duality, if you note down the various points of duality between the two, point number 1 is that TCR is a switch basically. Should I write it from here? I will write here duality between TCR and Gcse. The first point of duality is that TCR is a switch in series with a fixed inductor. Whereas Gcse is a switch in shunt, not in series but in shunt with a fixed capacitor. You already know this is your for example TCR, ये bus voltage है V, ये आपका TCR है. You have already studied it in module number 1. It is like this. GCR is basically a switch S in series with fixed inductor L, whereas Gcse, this is TCR. TCR is a switch in series with a fixed inductor L, whereas Gcse is a switch. It's also a bidirectional switch, but in place of SCRs we have GTOs, and in place of series inductance we have a parallel capacitance. So where TCR is a switch in series with a fixed inductor, Gcse is a switch in shunt with a capacitor. So it shows duality. Here switch is in series with inductor, here switch is in parallel with capacitor. So the two are dual to each other. That's point number 1. Point number 2, I will write point number 2 is that TCR is supplied by transmission bus voltage. TCR is supplied by transmission bus voltage, whereas Gcse is supplied by transmission line current, by transmission line current. You can very clearly see that this is TCR, it is supplied by bus voltage. It's connected across the bus and it is supplied by voltage V, whereas Gcse is connected in series with the transmission line and it is not supplied by voltage, it is supplied by transmission line current. So this is another point of duality between the two. Okay, this shows the dual nature of the two. So third point of duality is that TCR value is opened at current zero crossing. Current ZC means zero crossing, whereas Gcse value is closed at voltage zero crossing. You know, if you remember, just go back to the operation of TCR. Whenever TCR current becomes equal to 0, the valve can be turned off. It is opened. Whereas just few moments back you have seen in case of a Gcse, the valve is closed. It's turned on only when voltage becomes equal to 0. Okay, so this is another point of duality between the two. Okay, then next point of duality is that TCR current, which is IL as a function of alpha, is controlled. Since it is a function of alpha, it is controlled by turn on delay angle. Turn on delay angle alpha. Whereas Gcse voltage, which is actually voltage across capacitor, Vc, which is a function of gamma, is controlled by turn off delay angle. Turn off delay angle, जिसको हम gamma कहते हैं, gamma. Okay, we know you have already got the equation for TCR inductive current. TCR inductive current is a function of alpha. It is controlled by controlling the turn on delay angle alpha. Whereas in case of Gcse, just few moments back we have got the equation for GCSE, and you have seen that GC, in case of GCSE, this voltage VC gamma, it is a function of turn-off delay angle gamma. As gamma increases, the voltage across the capacitor decreases. As gamma decreases, the voltage increases. So it's a function of gamma, turn-off delay. So whereas TCR current IL alpha is controlled by turn-on delay angle. GCSE voltage, in case of TCR we control the current, whereas in case of GCSE we control the voltage. So voltage is dual of current. And current in case of TCR is controlled by turn-on delay angle, whereas the voltage in case of GCSE is controlled by turn-off delay angle. Here it is turn-on delay angle alpha, here it is turn-off delay angle gamma. So this again shows a dual point of duality between the two. And finally, last point of duality is that TCR controls the reactive current. ये IL alpha जो है आपकी ये reactive current है. In an inductive circuit, in an inductor supplied with fixed bus voltage and thus acts as a variable admittance. Let me complete this. Whereas Gcse controls the capacitor voltage supplied with fixed current, not voltage, fixed current, okay, and thus appears as a variable impedance, and thus appears as a variable impedance. TCR controls IL alpha, okay, and we know that TCR is supplied with fixed bus voltage, therefore it acts as a variable admittance. It's connected across the bus, across the transmission line, so it acts as an admittance but variable admittance by alpha control. Whereas GCSE is connected in series with the transmission line, and it controls the capacitor voltage, which is not supplied by it, controls the voltage across capacitor, and this GCSE is not supplied by the voltage, it's supplied by the fixed current, and therefore it appears as a variable impedance. So therefore, whereas TCR appears as a variable admittance, the GCSE appears as a variable impedance. So therefore the two are dual to each other. So because of the similarity between the two devices, between TCR and GCSE, or because of the duality between the two devices, between TCR and GCSE, the same equations which we have developed for TCR, okay, mathematical equations, the same equation can be used for defining the operation or behavior of GCSE. For example, the fundamental component of inductive current in case of TCR, we know that it is given by this equation. We have already derived it. If you remember, it is V by omega L times 1 minus 2 by pi times alpha minus 1 by pi sine 2 alpha. In case of TCR, this is the fundamental component of reactive current, which is drawn by the TCR, which determines how much reactive power a TCR absorbs. Because GCSE is dual to TCR. So in case of GCSE, what we are controlling? In case of TCR, we are controlling the fundamental component of reactive current. But in case of GCSE, we are controlling the fundamental component of capacitor voltage. So therefore, VC1, which is a function of gamma, it can be resolved since the two devices are dual to each other. We can use this equation for writing the mathematical equation for capacitor voltage VC1, fundamental component of capacitor voltage VC1 for a GCSE. In place of V, you have to write I because of dual nature, because of the duality between the two devices. by omega, because in place of L we have to write C. Then 1 minus 2 by pi, in place of alpha we have to write gamma, minus 1 by pi sine 2 alpha will be replaced by sine 2 gamma. So you don't need to perform the mathematical, although if you perform the same type of mathematical analysis here also, you will get this equation. But without wasting the time, without going for the mathematical derivation of this equation, you can directly write this equation from the equation of TCR, because of duality between the two devices. So therefore, fundamental component of voltage, capacitor voltage across a GCSC is given by I by omega C times 1 minus 2 by pi gamma minus 1 by pi times sine 2 gamma. Using this equation, we can draw this characteristic like this. This is gamma in degrees. For example, 0 degree, 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50, 60, 70, 80, 90. Because we know that the delay angle ranges from 90 degrees to 180 degrees. Or you can say 0 to 90 degrees. So that's why I have written 0 to 90 degrees. Okay. And this is Vc1, which is a function of gamma in per unit. This is the fundamental component of capacitor voltage as a function of turn-off delay angle. Okay, so this is, you can say, 0.1 per unit, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1.0. Okay, so it is something like this. This equation has various components. It is equal to I by omega C times 1 minus 2 by pi gamma minus this. So what is this? Is first term is 1. So this is 1.0. 1 to common rata, it is independent of gamma. So it remains common. So I have written here 1. Next term is 1 minus 2 by pi gamma. Okay? 1 minus 2 by pi gamma. As gamma increases, you can see as gamma increases, so this 1 minus 2 by pi gamma linearly decreases. It becomes something like this. ये है आपका 1 minus 2 by pi gamma. और तीसरी टर्म है इसमें 1 minus 1 by pi sin 2 gamma. और ये with respect to gamma ऐसे वैरी होगी. This is 1 minus 1 by pi sin 2 gamma. So this straight line, which is parallel to x-axis, it represents 1. This represents 1 minus 2 by pi gamma, and this represents 1 minus 1 by pi sin 2 gamma. And if you add all these graphs, this and this, you will get this graph. Let me show that with red color, something like this. ये आपकी final equation है Vc1, which is a function of gamma, which is given by this equation. So Vc1, which is a function of gamma, is I by omega C times these terms. These terms I have drawn separately. Adding up all these terms, you will get this. So you can see at omega t equal to 0 or 90 degrees, gamma equal to 90 degrees or gamma equal to 0 degree. The fundamental component of capacitor voltage is maximum. We already know that. And as gamma is increased, this decreases. And at gamma equal to 90 degrees or 180 degrees, it is 0. So range is 0 to 90 degrees or 90 to 180 degrees from the crest of the current. If this is current, ये 90 degrees है, 180 degrees. Range आपका gamma का 90 to 180 degree, or you can treat it as 0 to 90 degrees. Okay, so at omega t equal to 0 degree, it is capacitor voltage is maximum. It is like this, and as you increase omega, your capacitor voltage decreases. मतलब ये कम हो जाती है, ऐसे discrete हो जाती है और इसका magnitude कम होता है till you reach omega t. This gamma equal to 90 degrees. At gamma equal to 90 degrees, capacitor voltage is 0. So the continuous control of capacitor voltage, fundamental component of capacitor voltage, resulted. Okay, I hope this is clear. Now let us quickly discuss how we can use this GCSE. Now let me tell you that GCSE can be either used in voltage compensation mode or in impedance compensation mode. So first of all, I will discuss it in voltage compensation mode. If GCSE is used in voltage compensation mode, Okay, in voltage compensation mode, capacitor C is chosen, I will write here, in such a way that it produces the maximum voltage, capacitor voltage, which is equal to Vc max when minimum current flows through it. I mean into Xc. When you choose C, it will have certain capacitive reactance Xc multiplied by when minimum current is flowing through this capacitor. Then I mean into X will give maximum capacitor voltage. Now this I mean transmission line current, if it is at minimum value, now it can change. It can change from I mean to I max. Okay, and as the transmission line current increases, what will happen to the Vc? Vc will further increase, but you want to maintain it at maximum voltage, for which you have designed your Gcse for voltage compensation mode. You want that the voltage across this Gcse should be Vc max, which is given by this equation, corresponding to I equal to I mean transmission line current at its minimum value. So it should produce maximum compensation voltage, and that compensation voltage is placed in series with the transmission line, and it performs the series compensation that we already know. It provides the voltage support and all that. That means compensation. Now, but transmission line current will always not be at I mean, it will be variable. It can increase. As transmission line current increases, your compensation voltage may go beyond Vc max. We don't want that. We want that Vc should remain at Vc max. So therefore, as I increases, what we do is, whatever controller does, it increases gamma. And as it increases gamma, the current which is injected into the capacitor, that decreases. Transmission line current to increase hoti hai, but most of this current is bypassed through the valve by increasing gamma, and for less period the current flows through the capacitor. So the current injections into the capacitor decrease, so that this Vc remains at Vc max. This will be clear to you with the help of waveform. Let me draw the waveform like this. Let me draw the not waveform, in fact it's the characteristic, voltage versus current characteristic. Let me draw it. This is I, and this is the voltage across the capacitor Vc. Let us assume I is equal to I mean transmission line, when transmission line current is at its minimum value. Okay, let us assume capacitor voltage, capacitor is designed in such a way that it produces maximum voltage Vc max, and we already know that this Vc max is I mean into Xc, capacitive reactance. And as transmission line current increases from I mean to I max, we want to maintain this constant. हम इसको Vc max पे ही रखना चाहते हैं. Okay, we want that this is maximum voltage compensation voltage should remain constant. How can we do that? By increasing gamma. तो यहाँ से यहाँ तक, as current increases, gamma is also increased, so that less current is injected into the capacitor and this voltage is maintained constant. This is one thing. Another is that we can use this Gcse in impedance compensation mode. So another application is impedance compensation mode, not in voltage compensation mode, but impedance compensation mode. Okay, in the impedance compensation mode, the maximum reactance of the capacitor bank, that is equal to Vc max by Ic max. We first fix this, and then we can change this impedance also by gamma control, because this Xc basically is what is the capacitive reactance? It is voltage by current as per Ohm's law. Fundamental component of voltage which is appearing across the capacitor bank is Vc1, which is a function of gamma, divided by current is I. Okay, and as gamma is varied, this Vc1 becomes variable and Xc also becomes variable, so we can make it to appear as a variable impedance. So this is how we use this Gcse in impedance compensation mode. And of course, in impedance compensation mode, the characteristics are like this. This is Xc max and for example here this is IC max or I max, and here the voltage across capacitor is VC max. Okay, now what about the losses? Let me on this graph itself show you the losses. This is current through the GCSE versus power losses. Okay, let me first of all draw, then I will explain. These are power losses for VC gamma, VC1 gamma, capacitor voltage, fundamental component which is a function of gamma equal to 0, and these are for VC max. You can very clearly see VC1 gamma equal to 0. What does VC1 gamma equal to 0 mean? When will be voltage across capacitor equal to 0? When gamma is equal to 0. When gamma is equal to 90 degrees. When gamma is equal to 90 degrees, the switches are always on. They are not blocked. All the current is bypassed through the switch. No current flows through the capacitor, and capacitor voltage is 0. और जितना आपकी ट्रांसमिशन लाइन करंट फ्लो होती है, ये देखिए, let me try to explain it like this. It's very easy to understand and very interesting as well. When you make gamma equal to 90 degrees, the transmission line current either flows through G1 if it is positive, or it flows through G2 if it is negative. It does not flow through the capacitor because you are not turning off these devices. Gamma equal to 90 degrees means you are not turning off these devices. So current always flows through the switch S, GTO switch value. So since no current is flowing through the capacitor, capacitor is shorted by the switch because switch is permanently on, VC is equal to 0. So VC1 gamma is equal to 0. And since all the current flows through the GTO switches, as transmission line current increases, the current has to flow through these GTO values, so power losses in these switches will increase. So that's why I am showing that as the transmission line current increases from 0 to maximum, I max, the power loss increases. This curve shows power loss. However, if you want to use it in the voltage compensation mode, this is your, यहाँ से यहाँ तक आपकी सारी maximum current flow होती है through capacitor. Okay, you adjust gamma in such a way that this I min, or you block this. आप इसको block ही करते हो. You make gamma equal to 0 degree. When you make gamma equal to 0 degree, that means the valve is off. All the current flows through the capacitor in such a way that it produces maximum voltage VC max. Okay. VC max जब ये produce करता है, which is equal to I min into XC, and losses, since the current flows through the capacitor, and as the current flows through the capacitor, losses will be constant. Okay, the losses will be constant, almost constant, minimum losses, क्योंकि capacitor के through capacitor में losses minimum होती है. Maximum losses are when this current is flowing through valves, क्योंकि valves में switching conduction losses होते हैं. इस पॉइंट के बाद आप क्या करते हो? इस पॉइंट के बाद आप as your current increases from I min to I max, you increase gamma. आप gamma increase करते हो so that some portion of the current flows through valves and some current flows through the capacitor. Earlier at gamma equal to 0, all the current was flowing through the capacitor and losses were minimum. After this point, I min to I max, in order to maintain VC max constant, you are increasing gamma. You are making gamma greater than 0 degree in such a way that the current injection through the capacitor bank decreases and capacitor voltage is maintained at VC max, which I have shown here at VC max. And since now most of the current is flowing through the valves, so power losses will increase. यहाँ तक power losses कम है, उसके बाद power losses increase होती है. This is in voltage compensation mode, power losses, and in impedance compensation mode, which is like this. Let me show you the losses. This is XC gamma equal to 0, and this is XC max. अगर आप चाहते हैं कि the capacitive impedance should be 0, I have to draw it again. Then no current should flow through the capacitor, so that this capacitor does not come into the picture. All the current should flow through the GTO valves. और वो ये, this is the condition, xc gamma equal to 0. That's possible if all the transmission line current flows through the switch. So ये off ही नहीं करते आप ये switches. So as current transmission line current increases, the losses increase. लेकिन अगर आप चाहते हो that this should act as an impedance, okay, then part of the current should flow through this, and or most of the current should flow through this, so that it acts as an impedance and comes in series with the transmission line. तो उस केस में since current is flowing, most of the current is flowing through the capacitor, और capacitor bank में losses कम होती है as compared to GTO values, so losses will be minimum. So this shows variation of losses with transmission line current for both voltage compensation mode as well as impedance compensation mode. And finally, one more very important point, you have to note that for gamma greater than 0 degree, जब gamma greater than 0 degree हो जाती है, आपकी capacitor voltage becomes discrete in nature. Discrete in nature. See, for gamma equal to 0 degrees, capacitor voltage is maximum and continuous. Continuous जब है तो ये sinusoidal भी है. It's sinusoidal because I have already shown you gamma equal to 0 means आप GTO switch को on ही नहीं करते, ये off रहता है, तो आपकी capacitor voltage continuous है, आपकी capacitor voltage VC और ये transmission line current है, it is maximum and it is sinusoidal, so it does not have any harmonics. लेकिन जो ही आप gamma greater than 0 degree बनाते हो, for example in this case you are turning off your GTO somewhere here, तो voltage ये है, इससे पीछे GTO ऑन था, फिर ऑफ यहाँ करते हो, इससे कैपेसिटर वोल्टेज VC, और उसके बाद फिर से GTO ऑन करते हो और यहाँ ऑफ करते हो, तो आपकी वोल्टेज जो है it becomes discontinuous, it decreases and it becomes discontinuous. Discontinuous means, discrete means it has harmonics, okay. So VC contains strong harmonics for gamma greater than 0 degree, and so therefore the RMS value of nth harmonic component VCN, which is a function of gamma, it is given by 1 by omega c into, it is same equation that we have written for TCR current, उसी का dual आप यहाँ लिखिए, it is 1 by omega c times 4 by pi times sine, there it was sine alpha, here it is sine gamma, into there it was cos n alpha, here it is cos n gamma, minus n cos alpha will become n cos gamma, into sine n alpha will become sine n gamma, divided by n into n square minus 1. So if you plot this using a simple 2 or 3 line MATLAB program, the 5th harmonic component of voltage, 7th harmonic component of voltage, you can make n equal to 5, 7, 11, 13, number of harmonics, और so सारे harmonics of plot करोगे with as a function of gamma. Gamma you can take 0 degree to 90 degrees in small steps, so you will get all the waveform for, you will get the graph for 5th harmonic component of voltage, 7th harmonic component of voltage, 11th, 13th and so on, okay, where what is n? N is equal to 2k plus 1 and k is equal to 1, 2, 3. For example, for k equal to 1, n is 5. For k equal to 2, n is 7. For k equal to 1, n is 3. For k equal to 2, n is 5. Then for k equal to 3, n is 7 and so on, okay. And finally, just like in TCR, we have segmented TCR. The concept of segmented TCR is that instead of using only one single TCR, why not to use a number of TCR, one TCR and number of TSRs in series, in parallel, so that the harmonic content is drastically reduced. So similarly, on the same pattern, to attenuate harmonics, I will write here, to attenuate harmonics, discrete control of Gcse is used just like a segmented TCR. segmented TCR. It is something like this. You can note down, it's something like this. Instead of using one GCSE, we are using a number of GCSEs like this. These are GTO switches like this. ये आपका पहला GTO है, GCSE है, दूसरा GCSE आपका ये है, and so on. This is S1, this is S2, so on Sn. This is VC1, VC2, so on up to VCN. इसमें हम देखिए क्या करते हैं. If there are n number of, say n is greater than or equal to 2, okay, 2 or more than 2 GCSEs are put in series like this. If you have, say, for example, 5 GCSEs in series, out of 5, 4 are permanently off or permanently on. Okay, 4 are off, permanently off. Permanently off means the GTO value is off. या 4 इसमें permanently off होंगे or off, which means GTO value is on. जब भी GTO value ये for example off यहाँ होंगे, सारी current capacitor banks में से flow होगी and maximum voltages will appear across all these capacitors. या अगर आप सारे GCSEs off करेंगे, then that means these valves are on. Valves जब on है तो सारी current यहाँ से bypass होगी, voltage across these capacitors will be 0. But depend करता है आपकी requirement के हिसाब से. Out of 5 GCSEs, 4 you are either keeping all on or all off depending upon the requirement. और जो 5वां आपका बचता है ये, उसका आप gamma control करते हो and you perform gamma control of 5th GCSE. Since 5 में से 4 को आप permanently on रखते हो, तो उनमें से on मतलब अगर उनमें GTO valves off है तो कैपेसिटर्स में परमानेंट कैपेसिटर वोल्टेज ऐसी ही होगी. इसके अक्रॉस कैपेसिटर वोल्टेज कंटिन्यूस होगी और मैक्सिमम होगी, इसके अक्रॉस भी, चारों के अक्रॉस साइनोसॉइडल. और 5वां जो हमारा बचता है उसका हम गामा कंट्रोल करते हैं और उसके अक्रॉस वोल्टेज डिस्क्रीट होगी, नॉट ऑल द 5. So what will that do? That will achieve a lot of, there will be a lot of, see the rating of this GCSE will be 1 by m times the total rating. That is one thing. And second thing is that harmonic content will be reduced by a factor of 1 by n. Harmonic content is reduced in capacitor voltage by a factor of 1 by n, where n is the number of GCSEs. Okay, because if you are using 5 GCSEs, 4 उसमें इस तरह की वोल्टेज प्रोड्यूस करते हैं साइनोसॉइडल, बिकॉज दे आर परमानेंटली ऑन, और 5वें में आप गामा कंट्रोल करते हो. सो the harmonic content in the voltage is drastically reduced by a factor of 1 by n, where n is the number of GCSEs in series, और आपकी filtering requirements कम हो जाती है. And finally, since GCSEs are connected like this, there is no coupling transformer. They are not connected in series with the transmission line through coupling transformer. They are directly connected. So these valves are at very high voltage. Capacitor is also at very high voltage. Transmission line level voltage. And इनका जो controller होता है, control scheme, the controllers are generally placed on the ground and they have to be properly insulated against this high voltage. So that is all about GCSE. So therefore we have seen that GCSE acts as a variable voltage capacitor, variable capacitor or variable impedance. So it can be used either in the voltage compensation mode to inject variable voltage in series with transmission line, or as a variable impedance, impedance compensation mode to act as a variable impedance in series with the transmission line, so that the series compensation can be very easily done, and the control parameter with the help of which we can do the compensation control is gamma, which is called turn off delay angle. And there is a lot of similarity or duality between TCR and GCSE. So the same equations which we have developed by developed for TCR can be modified and used for GCSE. And then just like segmented TCR, we are using discrete control of GCSEs. Instead of using one single GCSE, we use a number of GCSEs, and that way the harmonic content is reduced by a factor of 1 by n. So that's all about this GCSE. So I hope it is clear to you that how a GCSE performs this series compensation, how it acts as a variable impedance. So I advise all of you to go through this lecture. All the best to all of you. Thank you.